Reflection, refraction, and dispersion of light. This is from Isaac Newton's work on optics, and that's how it was spelled back then. Light is made up of tiny particles called corpuscles. Light is reflected by some surfaces, and the angle of return equals the angle of incidence. Light can be refracted. It's another word for bent, as it passes from one medium to another. White light can be separated by a prism into many colors, but each specific color cannot be separated. All these properties are explained nicely by the particle theory of light. The law of reflection. The angle of incidence is equal to the angle of reflection. Both angles, here's theta incident, here's theta of reflection, are measured from a line drawn normal to the surface. And please remember, normal means perpendicular. So if a light ray comes in like this at a certain angle, it will bounce off the surface and reflect at the exact same angle. Those two angles are equal. We'll use these arrows or rays to indicate the direction that the light is moving in. Here we'll look at it sideways. Light originating from point P is incident on the vertical surface M and reflects with the same angle as the incident angle. These two angles are equal. And here's a nice example of the Matterhorn reflected in a lake. I think this is the real one, and down here is the reflection. Whether we think of light as a particle or a wave, it travels at a certain specific speed, 3 × 10⁸ meters per second. Actually, it's 2.99792,458, etc. times 10⁸ meters per second, but it rounds off very nicely to a 3 here. We use the letter C to denote the speed of light in a vacuum. If the medium that light is traveling through changes, then the light speed will change as well. And we can calculate the wavelength or frequency of light in a vacuum by using this equation here. C is equal to lambda, which is the wavelength, times F, which is the frequency. Refraction, not reflection now, this is refraction. When light transits from one media to another, for example, air, which is out here of the glass, to water, which is inside the glass, the light bends. So over here, this is a picture of a stick in a glass of air, right? It's right above the water. Then it gets pushed into the water. So this is a stick in glass half filled with water. They then superimpose those two pictures. The image under the water is shifted, okay? Right here, that's the shift. That when it's under the water, it looks like it's in a different place. When it was just in the air, it went straight like this. Now clearly the stick is not bending, so what's going on here? When light is incident on a new medium, some of the light reflects. If the medium is transparent, some of the light will pass through into the new medium. And how much reflects and how much goes through is dependent on the materials, the media. So we'll do the easy part first. Incident ray hits here, reflects with the same angle, okay? So that's going to be our reflection. Now, what's happening when it goes through the water? The light passing into the new medium is bent or refracted. The angle the refracted ray makes with the normal is called the angle of refraction. So there's our angle of refraction, and once again it's measured to the normal. And what do we have over here? If you come from the water and go up to the air, go like this, some of it's reflected. Again, this angle here equals this angle, and the other is refracted. It's bent away from the normal. When a wave passes into a new medium, its frequency remains constant, but its speed and wavelength change. Key point here, frequency stays the same. This is also true for light waves. The index of refraction, N, is a measure of how the speed and the wavelength of light changes when it passes from one medium to another. The frequency has to stay constant so that the waves do not pile up at the interface between the two media. The index of refraction is defined as the ratio of the speed of light in a vacuum to the speed of light in the medium. So it is a unitless number. Given that the frequency of a light wave is a ratio of its speed in a vacuum to its wavelength in a vacuum, we have frequency is c over lambda. In a new medium, where the speed of light is v1, which of course has to be less than the speed of light in a vacuum, right? This is the maximum speed anything can move. And the wavelength lambda 1 would be this. Frequency is v1 over lambda 1. Dividing these equations by each other and recognizing that the frequency stays the same in both media, we have c over v1 is lambda over lambda 1. And what is this term right here? That's the index of refraction of the medium. So we also have n1 is equal to lambda over lambda 1. Both the speed and wavelength are reduced by a factor of the index of refraction when light moves from a vacuum to a new material. The frequency of the light ray stays constant in all media. We've now said that several times, so hopefully that'll sink in, right? The effective speed of light in a medium other than the vacuum is slower than the vacuum speed due to the absorption and reemission of the light by the molecules in the medium. Because let's say you have water, okay, and you've got a bunch of water molecules. What's in between them? Absolutely nothing, okay? So light is absolutely traveling at the speed of light in between those molecules. However, when it hits a molecule, it excites it, and the molecule absorbs the photon. Then a little bit later, it re-emits it again when the excitation goes away and it goes back to its rest state. So if you take this speed here that includes when it was kind of stopped inside the molecule, that's why we call that the effective speed of light in a medium is slower. In materials other than a vacuum, the wavelength of the light ray decreases. The index of refraction is equal to 1 in a vacuum and is always greater than 1 in any other media. Here are some sample indices of refraction. As n increases, the speed of light and the wavelength of that light in the medium decreases. The index of refraction also depends on the wavelength of the incident light, and that contributes to the separation of colors in a prism, and we'll talk about that later. Because the index of refraction of air is so close to 1, for most calculations, we'll round that number to 1.
Dispersion, or light is made up of colors. Here we have a prism, glass or plastic prism, and we have an incident light beam, which is white. Basically, it's just normal light because light is white. As it enters the first surface here, it refracts. And you can see the line going through here, but something else interesting is happening here. The colors are starting to show. Then over here, the direction of the light bends again, so it refracts twice. Now, why did the colors come out here? Well, the index of refraction is wavelength dependent. So, for different wavelengths, for example, as the wavelengths increase, n will decrease. So there's less deflection from the normal line to the surface. This color separation is called dispersion. So if white light was just white light, you would just see a pattern like this. It would hit the prism, it would refract once, then it would refract again. But what's happening is light is made up of different wavelengths or different colors. Each piece will have a different refracted angle, and this gives us this beautiful looking separation of colors on the other side of the prism. Here's a chart that shows the refractive index, or n, versus the wavelength of incident light in micrometers, for different substances. For example, here's fluoride crown glass, borosilicate crown glass, etc. Different types of glass. So you can see, depending on the wavelength of the light, you get a curve here. The smaller the wavelength, the greater the index of refraction. Now, it has more of an impact. Let's say, look at here, flint goes straight, then it peaks up. Lanthanum down here, it's probably peaked somewhere up here. So the smaller the wavelength, the greater refractive index. In addition to a prism, which has this double refraction effect, which causes dispersion, which basically breaks the white light down into its many colors, we can also have a raindrop do the same thing. So this little blue bubble is a raindrop. We have light coming from the sun. It refracts once, and you can see the colors starting to separate here. It then refracts again, bounces off the raindrop here, get internal reflection, bounces here, refracts, spreads the colors out more, and you get enough of these raindrops, like millions and millions and billions of them, and you have a rainbow. Here's a little case where you're just shooting water into the air from a fountain or a sprinkler, and you can see the rainbow forming right there. So the droplets of water in the air act as prisms. This now sums up what Newton's optics explain, where we treat light as a particle. The next section will focus on light's wave behavior.
Light has a wavelength of 720 nanometers in air. It enters a glass prism with an index of refraction of 1.55. What is the speed of light in the glass? The givens are up here. Please ensure you convert nanometers to meters. 1 nanometer is 10 to the minus 9th meter. Here's our index of refraction. Here's the speed of light. Our index of refraction equation, speed of light in a vacuum over the speed of light in the media. We substitute in our givens. Well, first we isolate V, okay? So we multiply both sides by V, divide both sides by N. Then we put in our numbers, and we get a speed of light in glass is 1.94 times 10 to the 8th meters per second. And one way to check if that's correct, if you get any number for the velocity of speed in any media other than a vacuum is greater than 3 times 10 to the 8th meters per second, you did something wrong and you should check your work. Light has a wavelength of 720 nanometers in air. It enters a glass prism with an index of refraction of 1.55. What is its wavelength in glass? We list the givens up here. We convert nanometers to meters, although you're going to see we actually didn't have to do that this time. But let's go on with the problem. The index of refraction equation is N glass is equal to lambda air over lambda glass. So we solve that for lambda glass by multiplying both sides by lambda glass and then dividing through by N glass. Substitute in the givens, and we get a wavelength of 465 nanometers. So what's our assumptions here? We'll assume that the wavelength in air is the same as the wavelength in a vacuum because N air is so close to 1. Lambda air can be expressed in nanometers because the index of refraction is dimensionless, and lambda glass will be in nanometers. So we didn't have to convert to meters this time because there were no other variables that had meters in it that would have canceled out. Light has a wavelength of 720 nanometers in air. It enters a glass prism with an index of refraction of 1.55. What is its frequency in glass? Our givens are here. And again, here's the translation from nanometers to meters. So our frequency in air is the speed of light in a vacuum, or air, because we're taking that as a good approximation, over the wavelength in air. All we have to do is substitute in our givens. Here's the speed of light, and here's the wavelength. And this time you absolutely have to put it in meters. Why? Because you need this meter to cancel out with that. So you get a frequency per second or hertz. And we get the frequency in air is 4.17 times 10 to the 14 hertz. But we were asked for the frequency in glass. Well, it's the same. The frequency of light does not change when it moves between media. So the frequency of this light wave is 4.17 times 10 to the 14th hertz in glass.